In the previous video, we made the argument that for a critical point to occur, rather a potential maximum, potential minimum, or potentially neither point, requires that the gradient vector be equal to the zero vector. In translation, that means that the partial derivative with respect to x is zero and the partial with y is equal to zero. If only one of those is equal to zero, that means nothing in terms of it being a maximum, minimum, or neither. For instance, you can have a rolling kind of carpet-looking function where it maybe looks like this. And in this case, you might say that this is a maximum right around here, but suppose this actually bends upwards like this, then in one direction it could be a maximum, but in the other direction it may not be. Therefore, we require that both of these partials be equal to zero. Let's take a look at an example where we will demonstrate the use of this principle to find critical points. So example 2 says find and analyze the critical points of f of x, y equals this thing. So first I'll compute my partials, and the derivative with respect to x is 2x minus 2. The derivative of y squared, negative 4y, and 5 is 0 with respect to x. And then f sub y of xy is equal to 2y minus 4. Now we want to find the critical point, so we're going to set these equal to 0. So I'm going to say set equal to 0 and set this equal to 0. So when I solve the first equation, 2x minus 2 equals 0, this gives me an x value of 1. And when I solve 2y minus 4 equal to 0, I get a y value of, let's see, add 4 divided by 2, we get x equals 1, y equals 2. So what we can conclude is the point xy equals 1, 2 is a critical point. Now we don't yet know whether that's a maximum, a minimum, or neither of those 2 points, so we need to do some further investigation. Now, if we want to know whether this is a minimum, maximum, or neither, we can take a look at a table of values. So notice that in this table, right in the center of it all, or sort of in the center of it all, I have that's where my x is 1 and my y is 2, my z is 0. And what I want to do is look at the surrounding points. So if I look really close to x equals 1, x equals 0.9, x equals 0.8, and a little bit further to the right, 1.1 and 1.2, and then I also look at y values that are very close to 2, what I want to look for is what are the z values around points surrounding 1, 2, 0. Well, I see that all of them are in fact higher than 0. Here we have, when x is 0.8 and y is 1.8, we have a z value of 0.08. And of course you could plug 0.8 and 1.8 in for x and y into that equation, you should get 0.08. And in fact, we see that everywhere surrounding this point, all the z values are a little bit higher than 0. And so we suspect that this is a local minimum. Now it's going to be a lot harder to talk about global because we're talking 3D functions, and the 3D function goes off into infinitely many directions. Yes, we can change x here, we can change x here, but we can also change x this way, or sorry, rather change y this way, change y this way, or this way, but then we can also look at the values going in different directions of that point. So we really want to have some sort of stronger tool to be able to do this. Now here is a three-dimensional graph of that, and you can see that the point 1, 2, 0 is in fact lower than all the points surrounding it. Now this happens to be a paraboloid, and so we can make the argument that it is an absolute or global minimum, but the analysis that we do here in this table, and even by looking at this function, unless we're absolutely certain that this function never comes back down or never does anything funky, we can only call it a local minimum. So how do we know? How can we know? Well, we won't derive this because this requires a little bit of a more complex analysis. But just like there's a test in Calculus 1 to determine whether that point is a maximum, minimum, or neither. Specifically, we looked at the rate of change slightly to the left and slightly to the right of our critical point and determined whether the function was increasing or decreasing. Here we're just going to accept this for now. So suppose x naught, y naught is a point where the gradient equals the zero vector. So that means that both the partials are zero at the point x naught, y naught. And the reason we're using subscripts here is because x and y are variables. But when we say x is x naught and y is y naught, it's magically the case that we've fixed the value of x and y. So imagine that the z-axis is right here in the center and it's coming towards you at the screen. We're just looking at the xy plane. And maybe there's a point over here. We'll call that x naught, y naught. Now you can see here the conflict. X is a whole axis of values. Y is a whole axis of values. But x sub 0 is a specific value of x. It's specifically that distance right there. And y naught is specifically that distance right there. And that is the point at which we're claiming, for whatever this imaginary function is, that we have a critical point where both of the slopes are 0. So define this thing called capital D is equal to the second derivative with respect to x evaluated at x naught, y naught, that critical point, times the second derivative with respect to y evaluated at that point, minus the partial, the mixed partial at that point squared. Now the reason this is squared is because fxy and fyx are equal by our previous lesson. So really you can think of this as fxy times fyx, but since they're both the same, you don't have to use both functions. If d is bigger than 0 and the partial with respect to x is bigger than 0 at that point, then f has a local minimum at x naught, y naught. If d is bigger than 0 and the partial is less than 0 with respect to x, then f has a local maximum at that point. If d is less than 0, there's no other additional constraint. We can say f has a saddle point at x naught, y naught. And if d equals 0, I love this, anything can happen. We don't really know from the test itself whether that point, x naught, y naught, whether that point is a minimum or maximum or neither. So we'll use this test. This has to do with some linear algebra concepts called the determinant. We'll leave this as just a blue box test. And I want to demonstrate what a saddle point is. A saddle point, it looks like a saddle. And if you look at this red point here, then you can actually see that it's a maximum in one regard. In fact, it's a maximum. If you were to ride this curve this way, you can see that it's a local max, but moving in the opposite direction here, you can see that it's actually a minimum. And so when there's a point that's simultaneously a maximum in one direction and a minimum in the other, we call that a saddle point. So that is called a saddle point. Again, it looks like a saddle, and therefore that's what we call it. So let's verify, for example 2, that 1, 2, 0 is a local minimum of this function here. So we need the second order partial derivatives. We've already established that f sub x is 2x minus 2. F sub y is 2y minus 4. And now we find the second partials, f sub x. Take the derivative of this guy with respect to x, which is going to be 2. F sub y is going to be, f sub yy, is also going to be 2. And then we need the mixed partial derivative. Here this one already has the derivative taken with respect to x, so it doesn't really matter which one we differentiate, but let's take the derivative of this guy with respect to y. Well, it's a constant function, with respect to y, this function is going to be 0, and now we can form the value of d. So d is going to equal f sub xx times f sub yy. Those are already both constants. The x's and y's went away, so it doesn't matter what point we're at. The d value will be the same since f sub xx is a constant. And then minus the mixed partial squared, and so we get d is equal to 4. Now from the table, if d is positive, we also have to look at the second f sub xx at the point, which, remember, our critical point is the point 1, 2, and it's always equal to 2, so it doesn't really matter, but we see that d is bigger than 0, and f sub xx at 1, 2 is bigger than 0. And what conclusion can we draw from that? Well, from the table, if d is bigger than 0, and the second partial derivative at that point with respect to x is bigger than 0, then f has a local minimum. So we can confirm that the point 1, 2, 0 is a local minimum. And that's in agreement with what we found earlier, but this test allows us to make that more concrete without having to look at a graph of the function. Let's take a look at another example. This one we're going to do the same. We're going to identify the critical points. So we're going to compute the two partial derivatives constituting our gradient vector, and the partial with respect to x is going to be 2x plus y, and the partial with respect to y is going to be 2y, derivative of y squared is 2y, derivative of x squared is 0, derivative of xy is plus x. And notice that we have a system of equations now, so we have to solve 2x plus y is equal to 0, and 2y plus x is equal to 0. And of course, we're setting them equal to 0 because we want to determine where are the slopes in both directions equal to 0. That idea that at a peak, the tangent plane is going to be flat. I didn't do a very good job of drawing a flat tangent plane, but I think you get the idea that this plane here is going to have a slope of 0 in both directions. Now, when I solve this, I would have to solve by substitution because both the equations depend on both variables. So in order to do that, let's say for the first equation, we solve for y, and that means y is equal to negative 2x. So for the second equation, so just to make you aware of which equation we're using here, we're going to actually substitute in negative 2x for y. So we'll do 2 times y, which is negative 2x, plus x equals 0. And so that means that negative 4x plus x equals 0, which means that negative 3x equals 0, which means that x equals 0. Now at this point, when you solve a system of equations, you can plug that value of x, which you know 0 is a value common to both of these equations. You can find y by saying 2x plus y has to equal 0, and if you substitute in 0 for x, you get y is equal to 0. If you do the same thing here, but it's easier to do here in this equation because you've already got it set up in terms of y equals. So if you put in 0 for x here, you'd get y equals 0 as well. But if you use this equation, 2y plus x, if you substituted in 0 for x, you get y equals 0 as well. So at that point, it doesn't make a difference. So we know that the point 0, 0, 0, 0, xy is a critical point. And so we compute our partial derivatives. And so our second derivative with respect to x is 2. Our second derivative with respect to y is 2. And our mixed partial is going to be 1. And so when we compute this value of d, we're going to do 2 times 2 minus the mixed partial squared, which comes out to 4 minus 1, which is 3. And that's bigger than 0, so that's important. And when the d value is bigger than 0, we need to look at f sub xx at our point. Now, again, these are all constants. And we'll look at one more example in a separate video, and we'll see these don't always have to be constant. But when they are, that is equal to 2, which is bigger than 0, which is a local min. And there we go.